Analyzing the M+1 peak. We can use this M+1 peak to determine the number of carbons in a compound. And when we looked at this spectrum before, I pointed out that this tall one here is our molecular peak, and it has a mass of 16. There is an M+1 peak here that has a mass of 17. And so the peak at 16 is a carbon-12 plus 4 hydrogens. The peak at 17 is a carbon-13 and 4 hydrogens. So we expect this number to be about 11% of the base peak, because in nature, carbon-12 is 9%, and carbon-13 is 1.1%. So obviously methane only has one carbon, and this is going to be 11.1% of all methane molecules are going to have this odd carbon. If we look at something that's a bit larger, like benzene, we have the possibility that this carbon is a carbon-13. We have the possibility that this carbon is a carbon-13. That would make 2.2. This makes 3.3% chance, and on around. So we end up with 6.6% of the molecules have at least have a carbon-13 in place of the carbon-12. And that's what we find here. If we compare the M1 peak down here to the M peak, we'll find that it's a 6.6% difference. Now let's see how we can use this to figure out the formulas. So in this example, we've got the number of carbon atoms of an, that's not it, here it is. Propose the molecular formula of a compound from the following mass spec. So this is going to be our M, and this will be our M+1. So our molecular mass is 86, and our molecular mass plus 1 is here. And we can look at these. We need to figure out the ratio of M+1 to M. And we'll do that by taking the 1.2, this is the M+1 peak, and dividing it by the M peak. And that'll give us the relationship of them to each other. This is going to be times 100. Let's make it a percentage. And we come up with 5.7. So our M1 in relation to our M is 5.7. We'll need to divide that number by the percentage of carbon-13 in the environment, which will give us a 5.2, which we're going to round to 5. So we've got 5 carbons in our compound. And we know we have a molecular mass of 86. 5 carbons, 5 times 12, is going to give us 60. So that leaves us with, let me move this down. We've got 5 carbons present, so we've got 60 molar mass units for the carbon, and we have 86 as our total mass minus the mass of the carbons, gives us, let's see, 26. For the rest of the molecule, has to have a mass of 26. The 26 is an even number, and so we'll expect to have no nitrogen. Because it would have to be odd, and we don't have enough mass there for 2 nitrogens. The mass of 26 is too much to say that it's all hydrogen, so we can't do this because that's too many hydrogens. That won't work. So let's put an oxygen on here. Let's assume that we have 26 mass units left. Let's subtract off an oxygen, and that'll leave us with 10. So our compound is going to be carbon 5. We're going to have 10 hydrogens and 1 oxygen, and that's our formula. We can do this with data without getting the chart, just by giving us the location of the peak and its relative height. We can figure out the molecular formula for these 4 compounds. So we have a molecular peak that is 28.3% of the base peak, and we have an M+1 peak that is 1.7%. So we need to figure out how these two relate to each other. And so we'll take our 1.7 and divide by 38.3 times 100%, and that will give us 4.4. That's just percent. That gives us the percent of this M1 peak compared to the M peak. Now we'll need to divide that number by the relative prevalence of carbon 13, and we'll get 4. We're going to have 4 carbons in this compound. So 4 carbons will weigh 48 molecular units. Now we have a molecular mass of 72, so we'll take our 72, subtract off the mass of the carbon, and we'll end up with 24. So the rest of the molecule has to weigh 24 units. If we add an oxygen, that will leave us with an 8 here. So 16 is obviously the molecular weight of oxygen, and we're going to have 8 hydrogens. So our compound is going to be carbon 4, H, 8, oxygen. Okay, so here on B, we have a molar mass of 68, and this is 100%. This is our base peak. So we don't have to do this first step where we determine how they relate to each other because it's right here in front of us. The M+1 peak is 4.3% of the molecular peak. Okay, so we can start with our 4.3 and divide it by the prevalence of carbon 13, and we'll get, again, 4 carbons. And we're going to want to do the same kind of rationale we did before. We're starting with a molecular weight up here, 68. So we'll take 68 and we'll subtract off the mass of the carbon, which was 48, and that leaves us with 20. Again, we can't have a nitrogen, and we can't have 20 hydrogens. That's too many hydrogens for just 4 carbons. So I'm going to subtract off an oxygen, and that'll leave us with 4 hydrogens. So our formula here will be carbon 4. We're going to have 4 hydrogens and an oxygen. If we do the next one, again, the base peak is already in relationships, already been figured out. So we've got 4.6 divided by 1.1. That's going to be going to round out to 4 carbons. And we've got a mass of 54 minus 48, which is the mass of the carbon. And that gives us 6. Well, 6 mass units left is not enough to have an oxygen or a nitrogen or anything. It must just be hydrogen. So the compound formula for this is going to be 4 carbons and 6 hydrogens. Last one here, we have a mass of 96, and we're going to have to figure out the relationship of the molecular peak to the molecular plus 1 peak. So we're going to have to do our 1.5 divided by 19 times 100%, and that will give us, got it figured out. Actually, I don't. So I pulled out my calculator. It's 7.9. We'll take our 7.9 divided by the amount of carbon-13 in the environment, and we'll come up with a 7.1. So we've got 7 carbons in our compound. 7 carbons are going to have a mass of 84. 7 times 12 is 84. And we have a mass that we're starting with is right here, 96. So 96 minus 84 will be equal to 12. That's not enough to have a nitrogen or an oxygen or anything, so it'll have to be just hydrogen. We have 7 carbons and 12 hydrogens.